In this chapter, we will pick up where the last chapter ended and go through a host of calculations. Continuing the discussion, we're going to call the side load X kilograms. If I use this little red line here just to mark the bottom of where my free hub body is for reference, then I can see how much that moves down when I apply the weight. When that happens, the spokes on the drive side are stretched farther and their tension will go up to more than it was before, and so will the tension on the vertical component. On the non-drive side, the opposite happens. The tension on the non-drive side spokes goes down and the vertical component decreases also. My test wheels are all made with spokes of the same length. I have the same components, the same crossing pattern, and the same tension on the spokes. The only variables are the spokes themselves, their diameter and elastic modulus. These are the three spokes we're going to use, and instead of just saying X kilograms of mass, we'll make it 60 kilograms. For the first calculation, let's start out with the Supreme leader spoke. Here is my familiar formula for the elastic modulus. Right off the bat, I can substitute 200 gigapascals for the modulus because Supreme has been kind enough to provide that information to me. I need to convert my 60 kilograms into a force, and I can do that by multiplying 60 kilograms by the gravitational constant, and that gives me a total of 588 newtons, but that's going to be divided up over 12 spokes, so the force per spoke is 49 newtons. The question becomes this: if the tension on this vertical component increases by 49 newtons, how much will the tension on the spoke itself increase, given that it operates over that very small angle of 3.76 degrees? So the additional tension on the drive side vector, the increase in the total tension, is going to be equal to 49 newtons, which is the vertical component, divided by the sine of 3.76 degrees. And that's 49 newtons divided by 0.0656. And if I did this right, that should be equal to 747 newtons. So if my tension on the drive side spoke was 1,300 newtons before I loaded the wheel sideways, then it should increase to 2,047 newtons, which is the sum of 1,300 plus 747. One more picture to make sure we know what we're doing. We went from this picture that shows the position of the free hub body before the hub is loaded to this picture here after the hub is loaded. The tension on my drive side spokes is now more than 1,300 newtons, and the tension on the vertical component has increased in length as well. I'm going to shrink this image down to something a lot smaller to make room for calculations, because I know you won't want to miss any of those details. Let's first calculate the strain on the spoke at 1,300 newtons, and this is where it would be after I built up the wheel and had it tensioned, balanced out, and dished correctly. And this would be my formula, the modulus of elasticity formula that we've seen many times. I substitute the given value of 200 gigapascals into the equation. Rearranging that formula, I get this, and I can start substituting values for newtons and cross-sectional area. Here I'm converting the denominator into newtons per square meter, which is of course the definition of a pascal. And now I see I can cancel out my units, and when I do, I get that result, which I can express just as a decimal like this. Inside this blue box is a summary of what we just worked out. And if I started with a spoke of 260 millimeters at 1300 newtons, it will have elongated to 260.54. My new length, of course, comes from this calculation here. And coming from a guy who has built many thousands of wheels, I'm going to tell you that that is a very credible result. So it appears our calculation was done correctly. Let's run through the same calculation, a little faster this time, and see what the strain on the spoke is at 2,047 newtons, which is, of course, its build-up tension plus the additional tension added to it with the side load. Let's use the term L2 just so we can distinguish this length from L1 a minute ago. All these numbers are the same as before, except I have a larger numerator and I get a larger answer. The summary and the results. At 2,047 newtons, my original 260 millimeter spoke will have stretched to 260.85 millimeters. Let's run through the same calculations with the Supreme race spoke. The analogous results show us that in the case of the Supreme race spoke with a modulus of 230 gigapascals, if I start with 260 millimeters, then the length at 1300 newtons is going to be 260.57 millimeters. And the length L2 at 2,047 newtons would be 260.91. Lastly, we'll do the analogous calculations on the Supreme laser spoke. And for the laser spoke, the one with the highest modulus of 260 gigapascals, we see that at 1300 newtons, we have a length of 260.73 millimeters. And at 2,047 newtons, which is L2, we have a length of 261.16 millimeters. That's a lot of data we've collected, so we better organize it for ease of comparison. Let's make a table to tabulate all these hard-earned results. So we have across the top the Supreme spoke, the modulus of elasticity, the length of the spoke at 0 newtons, the length at 1300 newtons, and the length at 2047 newtons. You'll notice that there are 2 columns that I'm going to leave empty for the time being. My leader spoke with a modulus of elasticity of 200 gigapascals went from a starting length of 260 millimeters to 260.54 at 1300 newtons and 260.85 at 2047 newtons. The race spoke with a modulus of 230 started out also at 260, went to 260.57 and then 260.91. And then the laser spoke with a modulus of 260 went from also 260 millimeters to 260.73 and 261.16. Our elastic modulus for the leader spoke is the lowest of the 3, and it might be interesting to see what would happen to the strain of the laser spoke and the race spoke if the modulus of those was also 200 at those tensions shown. So we're going to make another table here showing the leader spoke at 200 and keeping that constant for all 3 spokes. You'll see what I mean in a second. For the leader spoke, since the modulus was in fact 200 already, that I get the same numbers I had before. The race spoke, however, instead of being 230, if it had been 200, would have stretched a little bit more at 1300 newtons and likewise at 2047 newtons. In the case of the laser, it would have been 261.05 millimeters instead of 260.73, and at 2047 newtons, the spoke, instead of being 261.16, would have been 261.50. Even though the cross-sectional area of the leader spoke, race spoke, and laser decline in that order, the amount of stretching of the spoke under load is not as much as it would have been had the modulus of elasticity not increased at the same time. One more table, I promise you, the last one for at least a while. Supreme spoke. The next column going from 0 newtons to 2047 newtons. If I had a constant modulus of elasticity of 200 gigapascals, what would be the percentage of lengthening? The next column from 0 newtons to 2047 newtons using the actual modulus of elasticity, the percentage lengthening, and lastly, the mass in grams of 64 spokes. With the leader spoke, the percentages, of course, are the same, 431 grams. For the race spoke, if my modulus of elasticity were kept constant at 200 gigapascals, that is the same as it was for the leader, I would see an increase in length of 0.37%, but with the actual modulus having increased at the same time to 230, my percentage of lengthening is less, it's 0.35%, and my spokes have a mass of 363 grams. In the same way, my laser spoke, if the modulus was constant, then I would have a 0.58% increase in lengthening, but with the actual modulus increasing at the same time, it's only 0.45%, and a mass of 273 grams. Let's do one more thing. We'll go back and take a look at this table, and specifically the Supreme race spoke. How would my race spoke of 1.8 millimeters of diameter compare to an aluminum spoke with 1.8 millimeters diameter when it only has an elastic modulus of 70 gigapascals? If it starts out at 260 millimeters, how much would it stretch at 1300 newtons and then at 2047 newtons? When I run that calculation out with the aluminum spoke with a much lower elastic modulus, I get more strain per unit of stress, and at L1 I would see a length of 261.90 millimeters, and at L2 263.00 millimeters. Hopefully you can see from this little example that if I used aluminum spokes in this wheel of a diameter of 1.8 millimeters, that with the low modulus of elasticity, even if the aluminum spokes have enough tensile strength for the wheel would be much too flexy from side to side. If I'm committed to using aluminum spokes, nevertheless, the only thing I can do is to make them behave better in the wheel, and I can only do that by increasing the diameter and therefore the mass of the spoke. As we run through these calculations, we can of course notice that if we keep the stress constant, then the modulus of elasticity and strain have a linear but inverse proportionality.